Welcome to ES 310 Lesson 25. Today we will be combining the material from the last two lessons to analyze behavior for rigid bodies in general planar motion, where they see both translation and rotation. More information on this topic can be found in Hibbler's Dynamics textbook, Chapter 17, Section 5. So, as a quick reminder, let's take a look at the kinematic equations for rigid bodies. We have a set of general equations that apply for all rigid bodies, which are the definitions of angular velocity and acceleration in terms of the derivatives of the angular position and the angular velocity, and the combined definition that relates the two of these. If we have a constant angular acceleration, we also have these three equations relating the position, angular velocity initially, and finally the constant angular acceleration and the time. We also have general definitions for the relative velocity of a point on a rotating body that relates then the linear variables s, v, and a to the rotational variables r, omega, and alpha. We can find the absolute motion of a point on a rigid body if we can relate through geometry the angular and linear motions. We can also write expressions of the relative velocity of 2 points on a rigid body through these two expressions. 2 lessons ago we looked at rigid body translation, where there is no rotation, which gave us a set of 3 equations relating the sum of forces in the x and y directions, or the n and t directions, being equal to the mass times the accelerations of the center of gravity in those 2 directions, and the relationship that the sum of the moments is equal to 0. We also, if you remember, using the kinetic moment equations, could write that the sum of moments in at any point were equal to the sum of the kinetic moments, the cursive m moments, kinetic moments at that point. In the last lesson we saw the equations of motion for pure rotation, so rotation around a fixed point, which is usually called O. And in this case, the center of gravity has circular motion around that point, and we can write that motion as the normal and tangential components of the acceleration and forces. And so we have the normal forces being equal to mass times the acceleration in the normal direction, which is omega squared times r, and the tangential forces being equal to the mass times the tangential acceleration, which is alpha times r. We also once again have the moments around g being equal to ig, which is the moment of inertia times alpha, or around the fixed point, the sum of the moments is equal to io, the moment of inertia around the fixed point, times alpha. The procedure used here was to draw a free body diagram, establish your sets of coordinates, which is how we start every problem, write these equations of motions, these 3 equations, and then use kinematics if necessary to get to the velocities and times. We talked about kinetic moments as well, which is this cursive m, which is defined as the moments that would be created if m times a were treated as an applied force and I times alpha were treated as an applied moment. Remember, these were non-physical moments, but that simplified our analysis in some cases and allowed us to find the moments around any point on a rotating and translating body. So today what we're going to do is combine all of that information and look at general planar motion. So it has translation, so these 3 equations apply. The sum of our forces in the various directions are equal to mass times the acceleration, and the sum of our moments, if it's purely translation, would be equal to 0. And then we have the rotation equations, which have our sum of forces in directions equal to mass times accelerations in those directions. And then we have the moment equations, giving that the moment around either G or O is equal to the moment of inertia around that point times alpha. For a rolling cylinder, this is a special case, which we need to remember that there is an instantaneous center of zero velocity at the point where that cylinder contacts the ground. Because we're not slipping, we're rolling, right? And so that point is not slipping relative to the ground, so it's moving with the ground. And the ground is not moving, and so that point has a velocity of zero. Then using that information, we can write our sum of the moments around that point, which would be the same as this equation, the sum of the moments around O, being equal to the moment of inertia around that point times alpha. And also remember, for a rolling cylinder, the center of mass has an acceleration equal to r alpha and a velocity equal to r omega and a position equal to r theta. The procedure here, as is typically true, is we start with drawing a free body diagram. We draw our inertial coordinate system, which could be xy or could be nt, and then we establish the directions for our acceleration and our angular acceleration. We write our equations of motion, which include both the translation equations and the rotation equations, test for tipping or slipping if we have friction, and then solve those equations of motion and apply kinematics if necessary to relate our answers to the velocities, distances, and times. So let's take a couple of examples of this type of motion. Often general planar motion looks like a rolling object. So an object that is rolling down a slope or something of this sort is both translating and rotating. So if we look at this tire that is rolling down the inclined plane, we can draw our free body diagram of this tire. We've got a normal force at the contact point with the inclined plane. We have a friction, which in this case is going to be the maximum friction before it starts to slip. So our friction is going to be equal to mu s times n. This is our limiting case for slip. Limiting case for no slip. Okay, so that friction is going to be acting up the plane. So this is friction and this is the normal force. And then we have the weight of the wheel, which acts straight down, the weight of the wheel. Alright, so now those are the only forces acting on this wheel, so we can write our three equations of motion. It says the sum of the forces in the x direction, some of the forces in the y direction, and some of the moments, and we will use the center of mass. So let's define the x direction as being up the slope and the y direction as being perpendicular to the slope. So in the x direction, our forces are going to be the component of the w acting up the slope. If this is theta down here, this is also theta inside the triangle. And so we have the component of w that is acting up or down the slope would be opposite that, so that is the sine of theta, and it is acting in the negative x direction. And then we have the friction, which is acting in the positive x direction. That's going to be equal to the mass times the acceleration of g in the x direction. Now this is a rolling without slip, so the acceleration of g in the x direction is simply equal to alpha times r. In the y direction, we have the normal force, which is positive, and the weight, which is negative. So the weight times the cosine, which is the adjacent theta is equal to mass times the acceleration of the center of gravity in the y direction, which is 0 because it does not accelerate perpendicular to its direction of motion. And we have the sum of the moments around G. We picked G. We could have also picked this point, which is our instantaneous center of zero velocity. But working with G, we've got the friction times R, which is going to give us a positive moment, and that's the only force on this wheel that's going to give us a moment. And that then is going to equal I around G times alpha. And I around G, if we treat this wheel as a cylinder, is equal to the mass times kg squared times alpha, where kg is the radius of gyration that's given in the problem. So we can now plug in numbers. We get that 30 times sine of theta plus the friction, which is 0.2 using the limiting case, times the normal force, is going to equal the mass, which is going to be 30 over 32.2 since they give us a weight, times alpha times r, which is 1.25. That's our first equation. Our second equation is going to be 30 times the cosine of theta, is equal to the normal force. And then our third equation is going to be 0.2 times n, so that's our friction, times 1.25 is our r, is equal to the mass, again, 30 over 32.2, times 0.6 squared alpha. And we have three equations and three unknowns, which then we can solve. We can't use our calculator directly. We will actually have to solve these because one of our unknowns is theta, which is in the sine and cosine. So this is a nonlinear system of equations. But we can take equation 3 and 1 and plug in for alpha. So we'll have equations in theta and n. If we do that, we get, simplifying it, so let's give these numbers. This is equation 1, this is equation 2, this is equation 3. So 3 and 1 gives us, after some simplification, that 30 sine of theta is equal to 1.068 n. So I solve this bottom equation for alpha, plug it in up here for alpha, crunch those numbers, combine it with the 0.2 for n, and we get this expression. And then we take this expression and put it into 2. Alright, so we solve this expression for n, plug it in here, and then we can write that equation then as a combination of the sine and the cosine, which would give us then that the sine of theta over the cosine of theta, which is equal to the tangent of theta, is equal to 1.068, which we solve using the inverse tangent to get that theta is equal to 46.9. We can take that theta then and plug it in and find the normal force, the friction force, and the other unknowns in the problem. The other common type of problem that we see as this general planar motion are objects that have multiple types of motion. So you've got an object on a string, for example. So there's no fixed point on this object because it is going to be swinging, but point B is also going to be moving along the string. So we know that point B is going to be on a circle with a radius of that string. And we have the weight pulling down, and we have the tension going to be pulling along this line, so in a direction of 30. If we write our equations of motion, as we would standardly do, so we're going to have this is x, that is y. So the sum of the forces in the x direction, the only force in the x direction is this tension. Right, so we have the tension, and the component of it that's in the x direction is going to be the cosine of 30. And then we have in the y direction, we'll come back to the accelerations in a second. In the y direction, we have the tension as sine of 30, also positive because it's going up, minus all of w, all of the weight that's pulling it down. This is going to be equal to mass times the acceleration of the center of gravity in the x direction. This is our center of gravity in the middle of the rod. And this then is going to equal mass times the acceleration in the y direction. We need our rotation equation. So the sum of the moments around G are going to be equal to, we've got the tension, the part of the tension that causes a moment around G is this perpendicular part, right? So that's going to be the y part, so T sine of 30 is the y part of the tension, times the perpendicular distance, which is half of the length, so 0.15, and that is going to equal I for the rod around its center of mass. So we'll write it as IG times alpha, and IG, if you look up on the table, the center of mass of a slender rod around its center is going to be, so moment of inertia around its center is 1/12 of the mass times the length squared times alpha, and the length is 0.3. So now we have three equations, and we have T, so this is three equations, and the unknowns are, we don't know T, we don't know AGX, we don't know AGY, we don't know alpha. So that is four unknowns and three equations. So we need more information, right? That more information is going to come from the relative acceleration equations, because we do know the direction of the acceleration at point B, right? Because it's going to be in the direction of motion. All right, so what we've got then is that it's moving along a circle, so this is the direction of V and A. So let's take a look at that relative acceleration equation that relates this B, where we know at least some information about the direction of our acceleration, and the acceleration of G that's showing up in these equations. So what we have then is that the acceleration of G is equal to the acceleration of B plus alpha crossed with r of GB minus omega squared of r of GB. Now, this is initially released from rest. If it's initially released from rest, this term is going to be 0. The angular velocity of our body is going to be 0 if it's released from rest, so we're left with this expression. AG have the two components we don't know, so AGX in the I hat plus AGY in the J hat is equal to acceleration of point B. We don't know the value of AB, but we do know its direction, so we can write it then as AB times the sine of 30 I hat minus AB of the cosine of 30 J hat, which gives us this direction. If this is 30, then this is also 30, and the x part is going to be the sine opposite 30, and the y part is going to be the cosine, the adjacent part. The y part is negative because it's going down. So then we have plus alpha, which is in the k hat direction, crossed with rg of B, so the position of G relative to B is going to be in the negative I hat direction, so this is going to be negative 0.15 I hat. We take this cross product, so positive K crossed into negative I gives us negative J, so this is going to be 0.15 alpha negative J hat. So now we can write these as two equations. So what we did here, this is two more equations, right? We've got the I hat part, which is AGX equal to AB sine 30. And we have the j hat part, which is AGY equal to negative AB cosine 30 minus 0.15 alpha. So we've added two equations, and we've added one unknown, AB. And so now with this equation and the 3 we had up here, we now have 4 equations, 4 unknowns. They are linear, so we can solve them using a calculator, plug in all of our numbers, and we end up with the answers to this problem.